Hello, welcome to my poster on sparse high-order Czech filtrations, which is a topic on which I have been working recently with Michael Boucher and Michel Kerber. I will try to give you an overview of what we have been doing. And to start, we want to understand what is the higher-order Czech complex. So, in order 1, the multi-cover is the region covered by balls around a given set of points. So at scale r, we look at the balls of radius r, and the region covered by them is the multi-cover. The nerve of this region, which is composed by adding vertices for each ball and edges whenever two balls intersect and so on, is going to be the Czech complex of order 1. Now, when we want to go to the higher order case, we consider intersections of k-balls. So for instance, here we consider the regions covered by two balls, and we call these regions lenses. Then this is the two-fold cover, and the nerve is going to be the second order Czech complex. And again, we can see that for each one of these regions we add a vertex, and whenever two regions intersect, we add an edge, and so on. And then if we look over the Czech complexes over all scales of radius r, we have the higher order Czech filtration. This relationship between the Czech complex and the k-fold cover makes it a very interesting structure to be studied. However, the size can become exponential in n to the k when we go to the higher order case. And this can be computationally very costly. So that's why we look over sparsifications of it. So a sparsification is just another simplicial complex where we reduce the number of simplices while keeping up to some change the same information. And the way we measure if we are keeping the same information is having the same barcode. So a barcode, as we can see in this picture, which I borrowed from another article, is just a series of bars. And each one of these bars represents a topological feature. So when we are looking at the zeroth homology group, we are going to have one bar for each connected component. And then when the scale is small, we have lots of connected components. And when the scale starts growing and things start getting connected, the number of connected components decrease. We can do this for any of the homology groups, and this is going to encode some sort of topological data about your point set. So that's why, when looking for a sparsification, we want to find a smaller simplicial complex that keeps more or less the same barcode. Great, so that's what we want to do. How do we actually do that? The main tools we use in our construction are the persistence nerve theorem and a notion of k-distance. Very crudely speaking, the persistent nerve theorem says that, given two covers that are similar enough, the nerve of these covers are also going to be similar. So therefore, what we actually want is to look for a cover that approximates the k-fold cover, so that the nerve of our approximate cover is an approximation of the higher order Czech complex. And furthermore, we want this new cover to induce less simplices, right? So the way we choose to do that is to remove points from the original point set. And in order to choose which points to remove, we use the notion of a k-distance. The k-distance is nothing more than the distance to the k-th closest point. So in this example, if this point Q is outside of the set X, we have that the one distance to X is just the distance to its closest point, the two distance is to the second closest point, and so on. Now, the way we use this k-distance to construct an approximate cover to the k-fold cover is the following. We can divide this construction in three main steps. The first step is to add the scale as a new coordinate. So that now, instead of looking at our configuration at each scale, we can look at it over all scales at once. Here in this example, we can see the balls growing around each point, and the lenses that they form are colored for the case of order 2. The reason we do this is so that the final construction can be seen as the nerve of a single space instead of a union of nerves. So now that we managed to see this as a single nerve, we want to start removing points. To do that, we first freeze some chosen points. So as you can see in this image here, and wait for them to be covered by other lenses. So here in this example, this point A had the ball around it growing up until a point where it was frozen, and then the size of all lenses involving A were kept fixed. That's why we now have this cylinder form. And we keep it fixed until other lenses, which are not colored in this image, but we can see here, cover completely the lenses involving A. Then, once that has happened, we can safely remove all lenses that involve A without changing the covered space. And that's exactly what we do in the next step. So here you can see the overall idea. So the lenses around A were growing, then we froze them. We kept them there until they were fully covered by other lenses, and after that, they just disappear, and while the other lenses continue growing. This method removes all lenses associated to a given point at once, and that's why we manage to get a size that's linear on the number of input points n instead of n to the k. And we use this cover of the space as an approximation of the k-fold cover. We actually managed to show that it is a 1 plus epsilon interleaving. There is an 1 plus epsilon interleaving between them. And therefore, we can apply the persistence nerve lemma and conclude that the nerve of our construction is actually a 1 plus epsilon approximation of the higher order Čech complex. So that was all I wanted to tell you today. I hope you had some fun.